So we would like to find a finite difference approximation of the problem that we get presented in 618. So what do we want to actually do? Well, in the end, what we really want to do is find the function u that satisfies, or we can say that solves, Poisson's equation. So that solves this equation. The second derivative with respect to x plus the second derivative with respect to y of u is equal to some function f of x comma y that we are given for x and y on the unit square, which is also what we call 0.0 to 1 and the interval 0 to 1 cross product with each other. So, and also where u is known to be 0 on the boundary of the unit square. So what we are asked to do is we want to solve this using a finite difference approximation. So we are looking for a finite difference approximation. Which has which truncation error? Well, according to the exercise, we want to find a finite difference approximation with truncation error O of h squared plus O of k squared, where this is, where h is the step size in the x direction and k is the step size in the y direction. So how do we tackle this problem? Well, as I suggested earlier, look in the book, look at section 6.2. And if you look long enough, in particular by looking at equations 6.13 to 6.15, then the answer comes to you quite naturally. But another thing that we can do together right now is to try to draw the grid that that we base our finite difference approximation on. So let's call this discretizing the problem. This is always the first step whenever we try to create a finite difference method, is to discretize the problem, i.e. draw a grid. So let's try to do that together. Well, we'll start with some axes over here. So I have, that wasn't a pretty line. So I have my y-axis and my x-axis. And then I have my unit square here. My unit square called d. And here I have 0, I have 1, and 0 to 1. And as mentioned earlier, we know the boundary values on the unit square to all be 0. And what we want to do is to start by making a grid. So let me try to do that. Well, so what we do when we make a grid is we divide our interval in the x direction up into a certain number of bits and try to imagine that these distances are all the same. And also we do so in the y direction. So this thing here will be my grid. And the grid that I've made has, well, the step size in the y direction I call k, and the step size in my x direction I call h. And according to the book, the way we index these different points along the x and the y axes, well, we index them by starting in x0 and ending in 1 equal to x capital N plus 1. And in the y direction, we start in y0 and we end in y m plus 1. Okay. So, what do we know? We know, I'll mark the points that we know with a violet color. We know the values in these points here. We know the values of u in these points along the boundary. We know that u is equal to 0 along each of these points. So, what are the names of these points? What are the indices? So, for example, this one is x1, y0, and this one is x2, y0. So let me just try to write down what do we know here. So by the boundary condition, we know the values of the following. We know the values of, well, u, let's see, we know all of these values here. So of u0, j, for all j ranging from 0 up to n plus 1. And we also know the values on this side here. So we know the values of u n plus 1, j, also for all j ranging from 0 to n plus 1. And also we know all the values down here, namely ui, 0 for all i's ranging from 0 to n plus 1. And we know all the values up here, which are ui, m plus 1 for all these i's over here. So all of these values here are equal to 0. So what's the reason we wrote this up? Well, probably this will help you guys when you are implementing the problem and you have to define the boundary conditions, in the sense that then you can define u to be 0 in exactly these points here. Yes? Okay. So what we want to do is we want to approximate. So what we want to do is we want to approximate the second derivative of u with respect to x and the second derivative of u with respect to y by using centered differences. And most of the work is actually done for you in the book. So again, section 6.2, look at equations 6.13 to 6.15, and think about your right-hand side. So is your right-hand side equal to 0, as it is in the book? Or is it equal to something else because of the way your equation is? Think about that. And I think that then you more or less have the key to constructing a finite difference approximation. The next step will be to draw a matrix and write up the matrix equation, and that will probably take a bit of work. So before you go do that, just make sure that you have drawn this grid, because this grid will help you so much doing this exercise, both the theoretical part and the programming part. And in the past weeks, people have also been asked to draw grids, and when people do not draw grids, what happens is often, well, then the implementation just gets really messy, and the debugging just gets really messy as well. And often it's very hard to come back and actually find out what you've done in your program. So draw the grid and watch the next video. And if you already feel that you're pretty sure about what's going on, then there's no need to watch the videos either. So that would be very nice. But yeah, then watch the next video.